let's wait 1 or 2 more minutes. There are a couple of students still missing. It's joining.
Professor, I have a quick question before we start. I am not able to download the homework now. I don't know what changed. Is there a way that you could re-upload it?
No, I heard there is a problem on Beachboard.
Yeah, I'm having the same issue myself.
Yeah, they say many faculty, they complain that some of the file cannot open. So I think university should be aware of that.
Okay, perfect. Thank you.
Yeah, so, but I think I uploaded last week. If you guys already download, it should be there. So, but double check after tomorrow or something. If not, let me know afterwards.
Okay,
Yeah.
thank you.
Yeah, I'll try tomorrow. I'll email you if it's.
Yeah, probably tomorrow. I think they should be able to fix. The file is there already last week. Thank you for raising up. Thank you, Erica. Any other questions or concerns? No? All right, so without further waiting, I think let's get started. Last week, we talked about a lot of example about Steger fastener. But here I would like to make a corrections in one of the notes that I have. Okay, so for these slides, if you want to use this equation, like I mentioned, you need to make sure the cross section is constant thickness. So this equation only applies for plates, not for angle, because for angle, the thickness actually you say is constant, but the shape itself is not constant. So somehow it's like this. Pardon me for the drawings, but somehow this is, you can see that at the end there's a rounded sort of circular angle on the end. So the whole cross section actually is not constant thickness, especially on the two ends. So do not confuse you for this equation only for plate. For others, like angle W and S, you use this formula. So let me make a correction here. So make sure you
just leave the math. I'll help you today.
Changes.
Leave it because you're just struggling.
Any questions?
I don't understand it. So I'll help you today when I'm done.
Okay.
I don't have Chris today.
If not,
so
let's move on to continue our example calculation
but do everything else,
for the Steger bolts. So last week we talked about this Steger fastener on the plate. Okay, on the plate. So, and then we talk about there are different failure path for this example. For example, ABTE and also ABCDE. So there are two paths. So if ABTE like this, then B and D are not Steger. So the calculation is very straightforward. So there's no Steger fastener. So there's no additional term to be added. But if you consider AB, C, D, E, then C and D is on the line of the stagger. So for C and D fastener, you have to use D prime. For bolt B, you need to use D only. So with that being said, you got 3 terms with a D, but plus 2 terms, S squared over 4G. So that's how you come up with this governing WN equation with net area 10.1 square inch. For this plate's constant thickness, if you want to, you can also use this formula, area, directly. If you want to, you will reach the same conclusion. I believe last week, I believe it's Gary, right? Gary Coker? Gary,
Yeah.
Are you there?
Yes.
Yeah, you asked me how come, why don't we just consider non-stagger, even with stagger fastener. We don't need to even edit this one. Because my answer to you is this: if in this case, if you do not consider this term, then you end up with. Let me see. If you don't consider this term, I believe this term is still governed. Okay, but for some other cases, this term may not govern. So it really depends. But the bottom line is this: you cannot neglect the stagger fastener effect. Otherwise, in some cases, you will be way too conservative in your design. Then somehow you waste a lot of money when you design the components. So that's why we still need to consider this D prime, S squared over 4G term in the stagger fastener effects. Okay, sometimes it may govern, sometimes it may not govern, but bottom line, you cannot be too conservative in your design. Okay, so I think I update my answer to you. Are you clear with that, Gary?
Yeah, so you don't want to be too conservative just because it'll cost too much. That's the main
Yes,
issue.
yes. So sometimes if it's stagger, you still need to consider the effect. Okay, even though it may not cover. Okay,
Got it.
okay. All right, so that's the update and a sort of review to what we ended up with last week. So now, today we will continue to different shape of tension member. For example, angle and S shape or W shape with stagger fastener. All right, so let's look at this example. If when the lines of bolts are present in more than one elements of the cross sections of a roll shape, and the bolt in this line are staggered with respect to another. For example, in this cross section, you have an angle 5 by 5 by half, and you got bolts in these elements. You have another two bolts in these elements, and also, unfortunately, these bolts
You're done. If you're done,
on this
you're
line and these bolts and this bolt, they are not aligned. They are staggered, as you can tell.
Did you
They
try
are
to do all your
staggered. So let
English?
me.
Everything
draw the
should be
line.
done. If you're telling me you're done
So
with
you
everything,
guys
then you're
can-
done with everything. Including your
So this
English,
is
every other class.
the line.
Okay.
In here, and
Okay, well then
This
email
is
and
the
make sure you
line.
completed everything and everything's
here.
turned in for all of your classes.
and this is the line
All of them.
in here. Okay. So, and also you can see that the bolts, they are not aligned, they are staggered when you talk about failure path. So if you need to use the area, equation 3.2 is preferred. Like I mentioned, A net is equal to AG minus T times T prime. So that equation is preferred to the net width approach instead of using W net. So like I mentioned to you. So if the shape is angled like this, you can visualize as a plate. So how do you visualize the angle as a plate? You can sort of unfolding this leg to this direction, unfolding. So unfolding means it will be like this. You unfolding. So this will become a plate, as you can see on the right hand side
how to find the area
of the figure
circle.
here. Okay,
On Khan Academy,
so
it
you
shows
can
you, and
do
on
this
YouTube,
way,
I
and
want
this
you to
can
watch the
simplify
video.
our calculation. So this way you can
How to
clearly
find the area
identify
of
the
the circle.
pitch, which is S, and also the gauge distance, which is G, in the calculation. So specification B2 specify any gauge line crossing the
How
heel
to find
of
the
the
area of the
angle
circle.
be reduced by amount
let that
that
one.
equal to the
That one
angle
should be good.
thickness.
That one too.
For
Whatever
example,
one you want.
the distance G between these two bolts, because they are crossing two different elements. So the G in this case would be 3 plus 2, but don't forget to minus the thickness, because you double count the thickness when you unfolding the angle. So just remember that the gauge distance G between these two bolts, when they cross different elements, the G here, when you unfolding, it will be 3 plus 2, but don't forget to minus thickness, which is ½ inch, because when you're unfolding, you double count the thickness already, so you need to subtract 1 thickness. So just remember this technique when you're unfolding, and the gauge distance should minus 1 thickness. Okay, any questions or discussions?
So that 4.5 is G.
Which one?
So G is 4.5.
G is 4.5 in this case. That's correct. Any other questions or discussions?
No, sir.
Okay. And also, in the following few lectures, when we talk about the design, I believe in one of your homework, last example, last problem of your homework too, you're about to design a bolt line with a tension member. And in figure 3.24 in the book, and also in the manual, part 1 of the manual, they give you the requirements. How many bolts you can fit in per element of the angle. Okay? So based on this chart, for example, how do you read this? If you only want to fit one bolt line, you're looking at the G, for example. Then if your angle is 4 from here to here, for example, let's look at this number. So if your leg is 4, and then you want to fit 4 inches, you want to fit only one bone line, so the G distance is 2.5. So that's by requirements. So likewise, if your angle leg is 5, then the G by requirement is 3. If you want to fit only one bolt line. And similarly, if you want to fit 2 bolts, 2 bolt line in one leg, okay? So as you can tell that because of the spacing requirements, the minimum leg dimension should be 5 inches. So here. So this distance from here to here, minimum should be 5. If the leg is 4 inches or less, you cannot fit 2 bolt line. So you want to fit 2 bolt line, you need to have a minimum 5 distance from here to here. So the G1 will be 2 inches and G2 1 3/4. So this way you can fit 2 bolt lines in one leg. Okay, so this give you the guidance about when you design and to pick your bolt lines, and they guide you the distance from the edge to the center of the bolt line. Okay, any other questions? Any questions? Discussions?
No, sir.
Okay.
So would that G value be like a minimum or a maximum, or does it have to be spot on?
It has to be spot on. That's by their requirement.
Okay.
Mhm. Because for this table, they already consider for whatever bolt diameter, they need to have a room for that. So they already consider all the scenario. So you have to be spot on for the distance. Okay. So now let's look into this example 3.7. We talk about an angle 8 by 6 by half with a stagger fastener in each leg. A36 steel is used, and the hole are 7/8 inch bolt diameter. Okay. Determine the design strength for LRT and determine the allowable strength for ASD. So in this example, you need to consider the yielding limit states as well as the fracture limit states, and to see which one govern. And the minimum one will govern the design strength for this member. Doesn't matter you are using RT or ASD. So yielding and fractures. Yielding is very straightforward. Yielding, we are talking about the gross area, AG, and times FY. So the trouble calculation will be in the fracture where we need to calculate an A net with a stagger fastener, as well as the shear leg effect as well, if available. So to do so, we will start with the calculation. So as you can see, that's A by 6. So based on this dimension in draw, you can tell that the distance from here to here is 8. From here to here is 6. Okay? Okay? And thickness of the angle is half. And this is a cross section. So the member, if you're looking from the side view, you will see this line is this line, and this plate is this plate. Okay? Then, and the loading is applied, tension load to the right, like this. So, solution. We need to calculate the fracture as well as the yielding. Let's start from the fracture one. So that one is more difficult and tedious to do. So before we do the fracture, the net area, we need to unfold this angle, become a plate. So that's the technique I just mentioned to you. So we unfold and become a plate like this. Okay? And the loading is to the right. So after you unfold, you see this similar to the plate. Then to calculate net area for fractures, can you guys tell me how many failure paths will be available?
I'm thinking just 2.
2. Which 2?
ABDF and ABCDEG.
And ABDF, so that's correct.
And then
And also
CDEG.
EG. Correct. That's perfect. That's great. That's great. All right. So with that being said, let's start to calculate the first failure path, ABDF. So if we talk about ABDF, so because B and D in this case, they are not staggered. So when you calculate the net, you need to use D for B and D instead of D prime. Okay, so the A net is equal to AG. So here is AG. So this should be AG. Okay. So it should be AG minus thickness of the angle times D or D prime. So like I said, for line ABDF,
it's so easy.
I've been telling you.
you only have D, not D prime, because those two bolts, B and D, they are not staggered. Okay, so what you need to do is 7/8 diameter plus 1/8 is 1 inch. We call effective hole diameter. Is the bore diameter plus 1/8. So 1 inch. So 1 inch is D, effective hole diameter, times TW is 0.5, and then you got 2 bolts. So you got 5.75
Oh, okay.
inch square.
On the phone.
Any question regarding this calculation?
Sorry, Professor, but can you explain how to get AG? How to get 6.75 inch square?
Which part you're not clear?
Just the calculation of AG.
This one?
Yes, sir.
6.75 is the gross area of the angle, 8 by 6 by half. So this one you need to check the menu,
Got it.
part 1 of the
Yes.
menu.
Yes, sir. Yes, sir. Thank you.
And TW is the thickness of the angle times effective hole diameter, which is 7/8 plus 1/8. In this case, you use D, not D prime, because on this line, ABDF, those bolts are not staggered. So you don't need to use D prime, just use D. You got 2, so times 2. So you end up with 5.75 inch square.
Thank you.
Mhm. So if you go back to here, like I mentioned, B and D, they are not staggered. So you need to use D instead of D prime in the calculation. Okay? Any other questions? No?
No, sir.
Okay. And then I think you guys already know the failure path. But in the book, he also showed this failure path. A, B, C, E, G in the calculation. Okay? But since you're already in my class, I told you that this one will not happen and it will not govern as well. But the book still do it to demonstrate, and this one will not govern. So let me tell you how come this one is not governed. So if you follow the failure path A, B, C, E, G for this failure path, as you can tell, the bolt B is not staggered, but C is on the stagger line. So for C, you got to use D prime. And E is not staggered. So E and B, when you use the equation, you need to use D only. But for C, you need to use D prime in the calculation. Okay? So with that being said, if you consider A, B, C, E, G, the bolt B, you need to use D instead of D prime. So this is clear. But for bolt SC, you need to use D prime. So this is D prime. For bolt C. For bolt E, you need to use D because it's not staggered. So you end up with 5.363 inch square. But remember, this failure path only account for 9/10 of the loads. So you got to times 10/9 to account for fully loaded 10 over 10 of the loads. So this will become 5.959 inch square. So this number is bigger than this one, ABTF. So usually this kind of failure path will not and will never cover. So that's why in my class, I told you last week, don't even need to spend time to calculate this failure path. Once again, how come you need to times 10 over 9 in this case? Because if you go back to this picture, AB, CEG, you only consider 9 bolts out of 10 to resist the fracture load. You are missing one of the bolts when it fractured. So to fully compare with apple to apple to the other failure path, like ABTF, which is fully resisted by 10 bolts. So you need to modify your answer by 10 over 9 in this calculation. Okay, so this just demonstrates to you this failure path will never cover ABCEG. Okay, so like you guys already know, the keywords, the key concept that I teach you in the class. Only when you fracture to no bolts will be left when you fracture on the connecting part. So that will be a valid failure path, like ABTF and ABCDEG. Other than that, it's not a valid path, meaning it will not govern at all. Okay? Are you clear with this? Any discussions?
Yes, sir.
So would that will always be the case, sir, when the net area is large, then the gross area, we don't consider that case as a governing equation?
The net area will never be bigger than the gross area. This is AG. Let me correct that. So this term is AG minus summation TW times T or T prime. So AG minus this is equal to A net. So for line ABTF, your N net is 5.75 inch square. But for line ABCEG, your net area is 5.959. So compare with ABCEG and ABTF, this one is smaller. Compare with this number. So which means ABCEG will never cover as a valid failure path. So that's what I mean. Okay?
Yes, sir.
Any questions? And also, when you calculate this S squared over 4G, A, B, C, E, G, so this is okay. So nothing is, this is the G is 2.5, and S is 1.5. So for this stackable D prime, when you consider failure paths like this is the G, and the S is this distance. Oh no, let me do corrections. The S is the S. So S is 1.5, G is 2.5. Okay, so any questions so far regarding these two failure paths? So you know that this one is not valid, A, B, C, E, G, with this demonstration, and it will not govern at all. So now, let's try another valid path we call A, B, C, D, E, G, meaning A, B, C, D, E, and G. So this is not a valid path. So when you do this calculation, which bolt you need to use D? Which bolt you need to use D prime? So let's starting from point A to B. So can you guys tell me, for bolt B, you use B, D, or D prime?
D.
D. Great. How about bolt C?
D prime.
D
D
prime.
prime.
That's great. How about bolt D?
D prime.
Also D prime. That's correct. How about E?
D.
How about D prime? How about bolt E?
D prime as well.
Also D prime.
But all those D primes are going to be different though, right?
Yes, they are different. That's correct. So the key concept you need to remember, whenever, for example, you starting from A, you draw the line. When this line is now stagger line, at the end of this line, you use D. And then when you go to this end of this line, it's stagger line. So this is D prime. At the end of this stagger line, D prime. At the end of this stagger line, so use D prime.
Professor,
Does
let's
it
just
make
say,
sense to you?
yeah. What if our our failure path start from G? Does it mean that E is
Same
going to
thing,
be?
you reverse.
Yes.
D prime, D prime, D prime.
Got
So
it.
this become D. This become D prime, and D prime. You still got 1D and 3D prime. Same thing. You're coming from backwards. This become D. And this is still D prime. D prime. And this is still D prime. So you still got 3D prime and 1D if you're starting from bottom up. Okay? Any questions or discussions?
No, sir.
So, because of this, as you can tell, especially between C and what's this bolt? D, right? For this path, you need to calculate S as well as, the G. And also the S. The S is between here and here. Okay, so the S is still 1.5, no change. But how do you calculate this G? based on our discussions? How do you calculate this distance?
Would be 4 3/4 minus the thickness.
It will be what?
Well, yeah, 5 and 1/4, right? The 3 plus 2 1/4 minus a half.
It will be 3 plus what? 2 1/4, right?
Yeah.
And then
The minus the thickness, so minus 1/2.
0.5, right?
Yes.
And what's this number?
The 4 3/4, which is what they're showing there.
This is how we get this number. Correct?
Yes, sir.
Uh-huh. Any questions? So this is how we get this number. Any other questions so far?
No, sir.
Okay, and then so the G between C and D is 3 plus 2 and 2.5 minus 0.5. That's what we just calculate. So the A net is equal to AG, the gross area, minus 0.5 for the first pole is D, and the rest of the 3 poles are D prime. But the G, S, they are the same in this case, but the G is different. It's 2.5, 4.75, and 3. So which is 2.5, 4 and 3/4, and 3. For the following 3 terms, G. So you end up with 5.015 inch square. Any questions so far regarding the A net?
No, sir.
So with this being said, can you guys tell me which one govern with all these 3 failure paths?
Would it be A, B, C, D, E, G?
Yes. So A, B, C, D, E, G will govern. So the A net is 5.015 inch square. So with that being said, the last case control. And because in this case, both of the leg of the angle, both legs of the angle are connected. So there's no shear leg problem. So U is equal to 1. So A is equal to A net, because U is equal to 1 in this case. So the nominal strength based on fracture is FU times AE is equal to 290.9. The nominal strength based on yielding will be Fy times Ag is 36 times 6.75 is 243 kips. Okay, so the design strength based on fracture is 0.5 times P nominal, 218. Design strength based on yielding is 0.9 times 243 is 219. So which one govern? Yielding or fracture in this case?
Fracture.
Fracture, so it's 218. Design strength per ART, and is a fracture govern. Any questions?
No, sir.
Okay. If you're using SD, like we mentioned before, the allowable stress for fracture is 0.5 U. This is per equation. It's 29 KSI. And times your effective area, which is you guys just did, 5.015 is 145. So this is allowable fracture load per ASD For yielding, allowable stress is 0.6 Fy per equation definition. So it's 21.6 KSI. So Ag is 6.75. So allowable loads for yielding is 146 kips. So with that being said, can you tell me which one govern? Yielding or fracture?
Also fracture.
Also fracture. So the allowable loads per SD is 145 kips. So this is the example demonstrate the angle with the Steger fastener. Okay? So if you follow what I said, the key concept that I covered in class, you can avoid calculating many unnecessary failure paths. So if you are not in my class, you will keep trying different failure paths. Maybe you can have, I would say 5 to 10 combination, but you will figure out that only 2 is valid in the end. Okay, so in the exams, if you can identify the valid failure path and do each calc and tell me which one govern, you will do. You don't need to demonstrate the invalid failure path. You don't have to do so during the exams and also in your homework assignments calculation. Okay? Any questions or discussions about this example?
Sir, I got one question.
Mm-hmm.
So, from what you're saying, we know that A, B, D, F, the straight line, can be a possible failure path. But then the A net is going to be larger than the one that we've been using for the A, B, C, D, E, G.
A, B, C, D, E, G. Okay, because this is a bigger number than this one.
Yes.
You need to find a minimum one. So this one govern. A, B, C, D, E, G will fail first.
Oh. Mm-hmm.
So meaning you will never reach ABDF in this case. This one will fail first because the A net is smaller based on A, B, C, D, E, G.
I understand.
Even though ABDF is also a valid failure path. So like I said, you need to pick valid failure path. And then you do calculation for each. And then pick a minimum A net as your governing failure path. That's what I mean. Okay?
Yes, sir.
Any other questions or discussions?
No, sir.
No questions? Okay. There's one more example, and this is the channel C6/13, and the bolt's diameter 5/8. Okay, so can you guys tell me how many failure paths available, valid, if the loading coming to the right? Valid failure path. Only one?
And I think there would be.
Think so.
I think there would be 2. Yeah.
2. Which 2?
A, B, E, and A, B, C, D.
And also
A, B, C, D.
A, B, C, D. That's correct. All right. And luckily, what's so lucky in this case? There are no what? Bolts on these 2 legs. Correct? So this will simplify a lot of calculation. So meaning you only have the bolts on this leg. So the A net, smallest net area, meaning you need to calculate ABE and ABCD A net and pick the minimum out of the two. So if you're working on ABE, your AG per manual for C 6x13 is 3.81 minus only one bolt. And this bolt is not stagger, so you use D, not D prime. So effective bolt diameter is 5/8 plus 1/8. So 3/4, you got 3.48 inch square. So this is failure path, ABE. If you're looking into the failure path, ABCD, then you have one stagger bolt, which is staggable at C, but non-staggable at B. So you follow the same calculation, but don't forget to account for S squared over 4G in this calculation. You got 3.30 inch square. So out of these two failure paths, this one will cover ABCD. So the smallest net area in this case will be ABCD. So this will be the governing failure path for this example. So any questions or discussions? So this is very, very straightforward example, similar to the angle, but luckily there are no bolts on the other two legs for this channel, C 6x13. Any questions?
I have a question.
Uh-huh.
How come ABCE is not a valid failure path?
It is the same as ABCD. The calculation is the same result. You can say ABCE because D and E, it doesn't make any differences in terms of this calculation because there's no bolts, like I said, because there's no bolts in here. If today you have a bolt at D or E, then it will make differences. Okay?
All right, thank you.
Mm-hmm. So luckily there's no bolts. So ABCD or ABCE, both will give you the same result. So it's a good questions. Any other questions?
No, sir.
Okay, so if not, I think I can stop the class at this moment. On Wednesday, we'll continue to finish up the Steger Fresnel with W shape and S shape with the Steger Fresnel, and then we will conclude section 3.5, and then later on we'll move on to block shear. Okay, so I will stay here for a few more minutes to answer any question regarding the today's lectures. If not, then I will see you guys next week. Okay?
Thank you so much.
Okay.
Thank you. Have a good day.
Professor.
Okay, bye-bye.
Professor, can you go back to the slide 34, I believe it is?